jet engines also have a strong effect on your longitudinal trim and stability. And so let's talk about why that is and how to account for that in our analysis. So here's a jet engine. Looks something like this. And we're going to use the axis of this engine. We're actually going to align it with the exhaust, the direction of the exhaust. So that's our axis that we're going to use. And then we're going to look at effects of the inlet velocity, which I'm going to call V sub I. And we're going to say that that's at an angle of alpha of J. That's the jet angle of attack. And then what's coming out the back here is V sub J. So a different velocity. And actually, I'm going to make these vectors, VI and VJ. So if we were to do a force balance around this volume here, we'd find that because the flow can be coming in at a different angle to the jet than it leaves at, it exerts not only the normal thrust and along the axis that we're used to thinking of for a jet engine, but it also creates a normal force that's in the same direction, just like a propeller. If we have a positive angle of attack here, then it's going to create a normal force out the top here, simply because it's changing the direction of this flow. It's inside of this system somehow. So we're taking momentum from one direction and we're changing the direction of that flow. So the force, the total force that is produced by this engine is equal to the mass flow rate times VI minus VE. Okay, and so usually we think of an engine as speeding up the flow, so it's making VE much faster than VI, and so because of that change in velocity, we get a lot of thrust, right? But those also have a direction associated with them, and that the change in the direction is what causes this normal force. So we get both a thrust component, which we can write as m dot of the jet times Vj minus Vi cosine of alpha j. And we get a normal force component. We'll call that n sub j, which is m dot of the jet Vi times sine of alpha j. Okay, so we can boil these down to the thrust and the normal, where the thrust is the force that is along this axis, and the normal is the force perpendicular to this axis in the direction of our angle of attack change there. So we're going to use a small angle approximation and say that this is basically alpha sub j, and that this is basically 1, okay? And then we can also actually combine these two equations to get rid of m dot j and write nj, the normal force, in terms of the thrust, okay? So if you do that, you get V infinity times the thrust over Vj minus V infinity times alpha j. So I've applied the small angle approximation and put the normal force in terms of the thrust itself. Okay, so now let's look at what this looks like on the aircraft. So we've got our center of gravity here, and then we're going to have our engine that's producing some thrust, and that is at some height. We'll call that h sub j, and it's sitting behind the center of gravity, a distance of Lj, and it produces not only thrust, but it also produces this normal force Nj. And now we can simply do a moment, figure out what the pitching moment is about the center of gravity due to the existence of this engine. And so the first term is going to be the thrust multiplied by this height, and then the second term is going to be the normal force multiplied by this length. And both of those, if they're positive, if all these terms are positive, will create a negative pitching moment. So we can say that the pitching moment at at the center of gravity due to the jet, it's defined as the moment from the jet divided by 1/2 rho v infinity squared SW c bar wing. That's how we non-dimensionalize the global pitching moment. And so when we plug that in, the moment of the jet is going to be minus the height of the jet, and we're going to bring that c bar w out front just like we did with the propeller, times the thrust, which we're going to use 1/2 rho v infinity squared SW. So that's the thrust times the height, minus LJ over c bar w times the normal force divided by 1/2 rho v infinity squared SW. Okay, so again, I'm just non-dimensionalizing these forces by the force here that we've used to non-dimensionalize, and then the length that we use to non-dimensionalize the moment, I'm linking with the length there. So that's just a preference for how to organize this. Okay, so we can actually, because the normal force is actually a function of thrust, we can plug that equation in there, and now both of these equations, or both of these terms in this equation, are a function of thrust. So we can bring that out front actually. So we'd have minus t over 1/2 rho v infinity squared SW times hj over c bar wing plus lj over c bar w times v infinity over, we got vj minus v infinity times alpha j, okay? So we've just swapped out that normal force for its relationship to thrust from this equation up here. Okay, at this point, it's helpful to recognize a couple things. First of all, let's look at alpha j, right? So alpha j is, that's the local angle of attack that the engine is seeing at the inlet relative to the, remember we've drawn our axis in the direction of the thrust at the exit, or the exiting velocity here. Okay, so it's the angle relative to that. And we can express that as our free stream angle of attack of the aircraft minus, plus a mounting angle, alpha naught of the jet. So a mounting angle of the jet relative to our fuselage reference line that is being used to calculate the free stream angle of attack. And then we can also account for the downwash from a wing. And of course, if this is sitting on an aircraft, it's sitting close to a wing most likely, and it's going to experience some downwash, especially from the main wing, or its relative position to the main wing. And so we'd compute that downwash, or estimate it the same way we would the downwash of a propeller sitting there, or another lifting surface in that same location. So that would be the downwash at the jet. And of course, downwash, as we know, can be written as some downwash at 0 angle of attack plus a gradient of that downwash with respect to alpha. Okay, so that's the same as we've always done. So this goes into there, and then this alpha j goes into there. Okay, another thing we want to look at is this term here, and it turns out that that term is related to the propulsive efficiency of the jet. The ideal propulsive efficiency is equal to 2v infinity over v infinity plus vj. Okay, so that's a definition for the ideal propulsive efficiency of a jet. And so we can actually rearrange this, and I won't work through the math, but we can rearrange this to write this term in terms of the ideal propulsive efficiency instead of the velocity at the jet exit. Okay, so when we do that, what we get here is that this whole thing. Well, actually, let's even take this one step further. Let's just go to our cm of j now, that the pitching moment coefficient of this jet is going to be equal to some pitching moment at 0 angle of attack plus the change in pitching moment with respect to alpha of the jet times alpha. Okay, so basically we're gonna split up this equation now after we substitute all these things in, and we're gonna get a constant term that's independent of angle of attack, and then we're gonna get a term that's proportional to angle of attack. And so what we get when we do that is that the constant term is equal to minus t over 1/2 rho v infinity squared SW times hj over c bar wing plus lj over c bar wing times eta, or the ideal efficiency, over 2 1 minus eta pi. That's the ideal propulsive efficiency. And then that's going to get multiplied by alpha naught j, so that's our mounting angle, minus epsilon d naught j, or the downwash at 0 angle of attack. Okay, so that's all of the stuff. That's our constant pitching moment. And then our pitching moment, or a change in pitching moment with respect to alpha, is all of the terms here, and these are from the jet, all the terms that are proportional to alpha, which is minus t over 1/2 rho v infinity squared SW times lj over c bar wing times our propulsive efficiency over 2 1 minus our propulsive efficiency times 1 minus epsilon dj comma alpha, or a downwash gradient at that location. Now, one thing that we did with the propellers that we can do here as well is these two terms here we can assume are equal to the drag. So that's actually a drag coefficient, or equal and opposite, or equal to our drag coefficient if the thrust is equal to drag. And so we can make that assumption, or if there's multiple jets on this aircraft, then it can be carrying, a 1/2 or a 1/4 of the load, depending on how many jets there are and how the thrust is distributed between them. So that's one simplification we could make. So one thing we learned here is that just like for propellers, a jet engine is stabilizing if it's behind the CG, and destabilizing if it's in front of the center of gravity. And then one last thing that I want to mention is that we've captured here what are often termed the direct effects of a jet engine. And so these are the forces and moments acting on the center of gravity due to the forces that are produced by the jet engine itself. There are many indirect effects actually that come from a jet engine, because this slipstream that's coming out down here can affect lifting surfaces behind it, and it can even entrain flow around it. And so if you have lifting surfaces even above or nearby this jet engine, they can see higher velocities simply because of flow entrainment. So these types of things, the slipstream behind or the entrainment, those are what we call indirect effects. They're much more difficult to capture in the early stages of a design. And so those are usually captured later when you're running full CFD or wind tunnel testing or flight testing and things like that, where you can capture those types of effects. But at this stage of the design, this is something that we can incorporate, are the forces of moments due to the thrust and the normal force that come from a jet engine.